We are Chicks in Space. We are an all-girls after-school science group that are composed of high school students. We are also members of the Neighborhood After-School Science Association, or NASA. That's NASA. We have learned a lot since we started working on the NASA Radiation Challenge last June. When we started this project, we knew very little about radiation and the danger it presents to astronauts. Astronauts are not allowed to accumulate a radiation dose that would increase their lifetime risk of developing cancer by more than 3%. NASA's goal is to keep radiation exposure as low as reasonably possible, or ALARP. The exposure limits for women are 20% lower compared to men, due to additional risk from breast cancer, ovarian cancer, and uterine cancer. Peggy Whitson, the former chief of NASA's Astronaut Corps, states that a female will only fly 45 to 50% of the missions that a male can fly because of the increased risk. As women hoping to be involved in the future of space exploration, the need for radiation protection became even more critical. This harmful radiation can damage DNA and lead to increased risks of cancer. Radiation has also been linked to weakening the immune system, cataracts, heart disease, strokes, and the development of Alzheimer's disease. As exploration moves beyond the International Space Station and low Earth orbit, we need to find a way to maintain radiation at ALARP, or as low as reasonably possible levels. Even on the ISS, astronauts are exposed to increased radiation. They are all equipped with personal dosimeters, which has led to the discovery that they are exposed to 80 to 160 millisieverts of radiation in 6 months, compared to only 4 millisieverts that is averaged in a person who is on Earth for 6 months. As Orion leaves the protection of Earth's atmosphere and magnetosphere, astronauts will be exposed to harmful levels of dangerous radiation. Exploration Test Flight 1, or EFT-1, is scheduled to take place in September 2014. Orion is scheduled to fly 3,600 miles above the Earth orbit the planet twice, and then splash down in the Pacific Ocean. It will be exposed to high levels of radiation. Space travelers face exposure to 2 types of radiation. Solar particle events, or SPEs, are explosions from the surface of the Sun that release radiation in ionized atoms. This type of radiation cycles with the Sun's sunspot cycle. Cycling space travel in times of low sunspot activity can be used to cut down exposure to SPEs. Galactic cosmic radiation, or GCR, comes from deep within the galaxy. A radiation protection system must be developed that will provide protection not only during space flight, but in future space colonies as well. One of the first projects we worked on during this challenge was the construction of a cloud chamber. This allowed us to observe the tracks of ionizing radiation that is ever present in our environment. Our research initially started using some government surplus Geiger counters and dosimeters. These worked well for some basic calculations, but we quickly realized we would need a more accurate way to measure radiation and develop a good radiation shield. We obtained a Vernier radiation probe, which detects and records alpha, beta, and gamma radiation. All Geiger counters contain a Geiger-Müller tube. This is a type of particle detector that measures ionizing radiation. We obtained radiation sources of alpha, beta, and gamma radiation. We concentrated our research on gamma radiation protection, as this is the most dangerous and difficult to block. We all agreed that our radiation shield should be simple, inexpensive, and as lightweight as possible. Because of the high cost of transporting materials in space, we also wanted our shielding material to be multifunctional if possible. There were constraints to our payload design. We considered the possibility of making an artificial magnetosphere or atmosphere, but realized this would be difficult and would not meet criteria for payload design in the challenge. Use of batteries or electric, magnetic, or other power sources is also prohibited. Our initial studies were aimed at calculating the halving thickness of various materials. This is a picture of our experimental design setup. We measured radiation counts for different depths of materials. We felt our experimental design was valid because we could reproduce known halving thickness values of water and packed soil accurately. We calculated halving thicknesses for various materials that would be staples on a space mission or space outpost. We also determined the halving thickness for simulated Martian and lunar regolith. We learned about the properties of graded Z shielding. Graded Z shielding involves laminates of materials with different Z values or atomic numbers. We also learned about Demron, a lightweight and flexible material made from a non-toxic polymer that offers the same radiation protection as lead shielding. We ran multiple trials using density blocks to see if there was a difference in shielding abilities, if the blocks were placed in different arrangements. We were able to document that layering arrangement affected the radiation shielding. We verified these findings using the student t-test. We wanted to develop a radiation shield that would be useful both during space flight as well as on future space colonies. We felt that shielding could be made of Demron sacks filled with essential food products and placed in containers of materials made in the graded Z shielding as a laminate. These containers would then be used as building materials for future space outposts. The containers could be filled with the regolith of the planet where the outpost was being established, and used in the construction of buildings that offered radiation protection. In order to obtain the maximum amount of information about the efficiency of different laminates of material, and in order to meet payload criteria, we proposed a nesting box design for our payload. We proposed making a 7-inch square box of thin aluminum. Inside this box will be eight 3.5-inch boxes that are each made of a different material. We were able to experiment with aluminum, lead, brass, copper, iron, and zinc. We will have nesting boxes of different materials to assess their effectiveness. We will use the graded Z shielding design. Inside the smallest box will be a sample of rice or beans, which we have found has the lowest halving thickness. In the center of each box will be the pill-sized dosimeter. If we were able to obtain samples of Demron, we would also like to include this in our experiment. We feel this box-in-box design will give us the greatest opportunity to test various combinations of materials to see which combination shows the greatest radiation protection. We also hope to further document the principles of graded Z shielding. Our design is simple, and we hope to obtain information about the most cost-effective and efficient laminate design for use as a radiation shield. We think our nested box design also allows for the added benefit of being multifunctional. After being used as a radiation shield during travel, the boxes can be filled with regolith and used in the simple and quick construction of space outposts that will also provide radiation protection and can be used to help maintain a stable temperature. We have learned a lot during the NASA Radiation Shielding Challenge. We hope to help the future of space exploration and possibly have the opportunity to travel to see the launch of the Orion spaceship. Thank you.